Welcome to the lectures on modern digital communication techniques. In the previous lecture, we have seen the relationship between the output of a bandpass channel when excited by the bandpass signal, and that relationship is straightforward for us because it's the outcome of a channel whose impulse response is given by Ht. That is what we have defined. So, output Rt is a convolution of St and Ht, and if we take the Fourier relationship, it turns out to be this. Now, we have already seen that SF has an expression which is SL of F minus Fc plus SL conjugate minus F minus Fc, and HF we have already defined here. That you can see we have already defined in the previous lecture. So, we will follow by the same thing. So, instead of the half, you simply have HL of F minus Fc plus HL minus F minus Fc. Now, if we look into these expressions, we could say that SL of F minus Fc is very close to 0 for f less than 0, and one could argue in a way that in some form one could say that SL of f is SF plus Fc, if you remember this. So, then you need to do this translation. So, one could have SL of f minus Fc should be equal to S plus of f. I would simply replace f by nu minus Fc. So, I am going to get this. So, this is equal to 0 for f less than 0, because we have taken only positive set of frequencies over here. So, that means what we are saying, that this value is very small or negligible as 0 for f less than 0. Similarly, if you would take this one, SL of minus f minus Fc, this value is also 0 for f greater than 0. That means very, very small, you could say. To argue on this front, you could also set up in a similar way that SL of f is equal to S plus f plus Fc, and then SL of minus f is equal to S plus minus f plus Fc, and then you could say that SL minus f minus Fc is equal to S plus of minus f, and if I would put f greater than 0, so you are going to get S plus of minus f, that means negative values, which is 0. So, that means this thing is nearly 0 for f less than 0, and this thing is nearly 0 for f negative. Similarly, if we go by the definition of h of f, what we have over here, what we see is that this is HF for f greater than 0, 0 for less than 0, and this quantity is 0 for f greater than 0. So, we could say that this is almost equal to 0 for f greater than 0, this is almost equal to 0 for f less than 0 in the same manner. Now, if we see these things, so for f less than 0, what we will find is only these two terms exist, right? Whereas, for f greater than 0, this term goes to 0, this term goes to 0 for f greater than 0. So, for f greater than 0, only these two terms exist. So, we could have this as half, that stays with us as SL f minus Fc. This gets multiplied with this HL f minus Fc, right? And for the other half, that means for f less than 0, we have SL conjugate minus f minus Fc. Sorry, this will be HL conjugate minus f minus Fc. Now, if we look at these relationships that are available with us, what we could say is that we could write this potentially as half RL f minus Fc plus RL conjugate minus f minus fc, right. So, in other words, we could say that where these relationships make sense if only we would define R L of f is equal to S L of f multiplied by H L of f, and therefore, we could see that we could relate this R of f over here and this is R of f over here to its low pass equivalent form in the same way, and since R L of f is related to S L of f and H L of f in this way, we can say that the low pass equivalent signal and the channel could help us in getting the passband spectrum of this particular signal. And since this is a multiplication in the Fourier domain, in the frequency domain, so what we have is R L of t, what we had defined before, we could write this as convolution of S L of t and H L of t. So, this is what you could write as the relationship between the two signals, that means the low pass equivalent in terms of the low pass equivalent signal and the system. So, that means this way we can say that if we take this relationship and if we would take this relationship that we have here with us, together we could say that you can find the outcome of the system which when excited by a passband signal. So, the channel is passband, the passband output is RT, and you could relate it through the low pass representation of the signal as well as that of the system. So, that means once again we have been able to show that given a low pass equivalent representation, you can well easily translate to the corresponding passband signals representation, be it in the time domain or be it in the frequency domain. One could also calculate and relate the energies of the low pass equivalent to its passband equivalent, right. So, we continue in this same mode, but now what we would like to do is we have to look at noise. Noise is very important. So, we said in the beginning noise is one of the important aspects. So, when you talk about noise, of course, what we are going to do immediately is not noise, we will apply our results to noise. So, you may think of noise as a stochastic process or the outcome of a stochastic process, and as a stochastic process you can describe it in terms of a random variable which takes values as a function of time. So, that means it is a time evolution of a random process. So, when we said noise, we will finally come to noise and we will see how is it represented and what are its relationship in the passband with that of the low pass equivalent and how do we take care of this. So, what we will consider is suppose Nt, let Nt be a sample function of a wide sense stationary. So, let me write this down in full, of a wide sense stationary stochastic process with. So, what we are writing, rather I would not put noise in this particular, we are going to discuss noise, but what we are going to do is representation of band pass stationary stochastic process. So, once we do this, we will find how noise relates to this description, and then whatever we derive in this particular thing would be directly applicable to that of noise. So, let Nt be the sample function of a wide sense stationary stochastic process, and we also state that this is 0 mean and power spectral density phi n n f. So, phi n n f is given, where we are saying that phi n n. So, we are writing phi n n to represent the power spectral density. What we could do is there might be a confusion of notation. So, we will put phi n n of f as the noise is defined in such a way that this is 0 outside an interval of frequency centered around f c. So, that means what we are saying is this phi n n of f is equal to 0 for f greater than f c minus w and for f less than f c minus w, and within this band, that means if there is a band w. So, within this band it has some values, right. What we are not saying that it is defined within this band, it is here, elsewhere it is 0, it means it is centered around this f c. So, we see that there is a lot of similarity with what we have done already before, except what we said, what we need to state is previously what we did. Previously we did deterministic signals, and now that we are handling here, we are talking about random signals. So, you may recall in one of the earlier discussions we said that how could you characterize signals. So, the previous section that we just did is about deterministic signals, and here since we are dealing with noise, we are talking about stochastic process which has its inherent randomness. We are basically talking about signals which are random in nature. So, we already have encountered some of the characterization of signals which we have started off with. So, in such a case, when this is what we have with us, we can write that NT could be represented as AT cos 2 pi FCT plus theta t. Now, this again holds true, which you could write in terms of xt cos 2 pi FCT minus yt sin 2 pi FCT, and again which you could write it as real part of zt e to the power of j 2 pi FCT. So, please note here that all that we have said here is this is a sample function of a signal which is band limited to w centered around f c, and w is much smaller than f c. So, it is a narrow band signal, and whatever be the signal, if it is narrow band and centered around f c, you could represent it in a form which is something like this, and of course, zt is the complex envelope, right, of this. So, now what we will deal with is, at this point we have said something. At this point we said that it is a wide sense stationary process, right. So, if it is wide sense stationary process, so we write WSS in short. So, since it is wide sense stationary, we would get this phi x of tau, which is the autocorrelation of the quadrature component, x quadrature component, x and y are the quadrature components of NT. So, we could write these two as quadrature components. Why we call it quadrature? Because this is on the cosine, this is with the sine. So, this is on these two, sine and cos, they are at quadrature 90-degree phase shifted. So, this is the, you can say, amplitude of this is the amplitude of the sine component. So, we call these the quadrature components of noise. So, phi xx is the correlation of the the I component, you can say, is equal to phi yy of tau, and you'll also get phi xy of tau is equal to phi minus phi yx of tau. What we'll do very quickly is we'd like to see whether this is true in very quick steps, and then we'll use this property to find use these relationships to find some important relationships between the passband and low pass spectrum, power spectral density, as well as the autocorrelation function of this noise. Now we should be careful at this point that if it is deterministic signal, we are dealing with the low pass representation of the signal and the passband representation of the signal. We are talking about the spectrum of the low pass equivalent, as well as we are talking about the spectrum of the passband. Now, if it is noise, you do not have a representation of the signal, you do not have a form of representation that it will evolve with time. So, in that case, we are rather interested in autocorrelation functions. We are interested in the power spectral density to represent or which characterize these processes. So, with the help of these, we will see how things are. So, we will start off with expectation of nt with n t plus tau. That means, we are taking the autocorrelation. So, this is the autocorrelation of nt. This is expectation, E is the expectation operator. So, expectation operator, it means that you are taking the ensemble mean, that means over the PDF. So, we have E, we would use this expression of this kind of a form, and we will be using that form to arrive at the autocorrelation and power spectral density. So, we have x cos x of t cos 2 pi f c t plus minus y of t sin 2 pi f c t, this is n t, and we also have x of t plus tau cos 2 pi f c t plus tau minus y 2 plus tau sin 2 pi f c t plus tau. This is what we have with us, and we are going to get an x with x multiplication, x with y multiplication, y with x, and y with y. So, when we have the x with x term, we are going to have x of t times x of t plus tau, and we will be having along with that the cos of t and cos of t plus tau. So, when we have this, this expectation operator would work on x t, because x t, as we see here, is the component of noise in the I phase, and y of t is the component along the this is along the I, this is along the q, right. So, when we apply expectation operator on n t, it would apply on this and this, because this is deterministic part. There is no randomness in this is completely deterministic, there is randomness in x of t. So, what we have done here in this representation, if it makes you confused, it is basically translating this x and y, which is the base band or low pass equivalent parts, to the pass band by means of this carrier, right. Things will be clearer a bit more later on. So, when we have this expectation operator, this will work on x t and not on cos. So, if that is so, we will have phi x x of tau is basically E of x t x of t plus tau. So, similarly, we are going to write all the relationships. So, what we will get here is phi x x of tau, I will write in short, cos 2 pi f c t and cos of 2 pi f c t plus tau. I will write this in short, and we will get along with that plus phi y, look at this y and this y, we are going to get sine of 2 pi f c t into sine of 2 pi f c t plus tau, and then you are going to get e of x and y, you are going to get this cross term. So, when you get this cross term, you are going to get a minus, and in this case also you are going to get a minus. So, we are going to get two terms, that is phi x y of tau along with sine of t and cos of t plus tau, and we are going to get another term phi y of x with cos of t and sine of t plus tau. So, this term x, you see there is a t. So, that means we are having this term and we are having this term. So, that means these two terms, right. So, these two terms make this particular product. So, what we have is expectation of y of t and x of t plus tau is written over here. Similarly, this term is a result of this and this. So, that is how this relationship come. At this point, we would have to use some of the trigonometric expansion. Cos of a times cos of b is half cos a minus b plus cos a plus b. So, I am writing this for cos, not another c, right, with the suffix, and sine of a sine of b is half cos a minus b minus cos a plus b, as well as sine a cos b is equal to half sine a minus b plus sine of a plus b. So, equipped with these things, and when we see this particular expression here above, this particular expression is sufficient for us. What we can say is cos of a plus b, that is here, we can expand in terms of cos of a minus b, cos of a plus b. So, then you are going to have cos of a minus b. So, where you are going to be left with a cos of tau, that means 2 pi f c tau, and the second term will be cos of 2 pi f c 2 t plus tau, because you are going to have this thing, right. So, we will be writing these terms accordingly, and what you can get is phi of n of tau, that is what we have here, phi of n of tau. This is phi n tau is equal to this, you can say this, right. So, that particular term, what we have before, would work out to half phi x tau plus phi y tau into cos 2 pi f c tau, and you are going to get half phi x of tau minus phi y of tau into cos 2 pi f c 2 t plus tau. Similarly, you are going to get other terms, phi y x of tau minus phi x y of tau times sine 2 pi f c tau, and minus of half phi y x of tau plus phi x y of tau into sine, in short I would write 2 t plus tau. We have said that n t is stationary. So, if we say that n t is stationary, then what we mean is that we said White's and stationary, that autocorrelation function of n t is dependent only on the lagged time and not dependent on time. That means, if we look at this expression here, this expression should not have any dependence on t. If n t is White's and stationary, the right hand side should not have any dependence on t. For it not to have dependence on t, this term and this term which have dependence on t should go to 0. So that means we can conclude from this, if this has to go to 0, this coefficient should be 0. So that means phi xx of tau should be equal to phi yy of tau, and if this coefficient should go to 0, then what we have is phi yx of tau is equal to minus phi xy of tau, and this is what we started off with when we talked about the white sense stationarity. So if you look at this, phi xx of tau equals to phi yy tau, phi yx of tau is equal to minus phi xy of tau. So minus sign goes on either side. So this is a very important result that we have for white sense stationary narrow bandpass process. So along with this, so if we are going to fit it back, what you are going to get is phi n tau. Now since these two are equal, so phi yy equals to phi xx, this is equal to 2 times. So we are going to get phi xx of tau. This term is going to 0 and this term is going to 0. So we are left with this. So you have phi yx is equal to minus phi. So you are going to have phi xy. So phi minus xy is equal to phi of xy. So you can say minus phi, we have a phi xx times cos 2 pi f c tau minus, because of this you are going to get phi yx of tau sine 2 pi f c tau. So then we proceed further and we could say that if we have z of t, remember our z of t, what we had z of t here, we had z of t there, that it is the complex envelope of n t. So definitely z t, you could write it as x t plus j y of t, and hence phi z z of t is equal to half z conjugate of t times z of t plus tau. So this is the way of defining, and what you would get, you could easily go through a few steps. You can get this as phi xx of tau plus phi yy of tau minus phi xy of tau plus j phi. This you could do a few steps. So that would mean phi z z of tau would be equal to phi xx of tau plus j phi yx of tau. So given this relationship, one could establish that, let us look at the last relationship that we derived. So if you look at this relationship that we have derived here, right, then you could say that phi n tau is equal to real part of phi z z tau e to the power of j 2 pi f c tau, right. So in other words, we are saying, so basically this is what we have. Yeah. So if you have phi z z tau is equal to phi x x tau plus this, so if you do this product, you are going to get phi, if you are going to take the real part of this product, you are going to get phi x x cos 2 pi f c tau minus phi y x sine 2 pi f c tau. So this is a form which is very similar to the relationship that you had when we discussed the baseband equivalent and the low pass equivalent and the pass band of a signal. So what we see in case of stochastic process, we basically have the correlation functions related in a similar manner that we have for the signal, and we have a similar thing for the autocorrelation function and its in phase and quadrature phase components. So we have discussed a few important properties of baseband signals and their passband equivalents. We have also seen the relationship of the autocorrelation function for the narrow band stochastic process. What we need to see now in the next lecture is the spectral relationship of the narrow band stochastic process and its relationship to noise. Thank you.